Sedimentary rocks are my favorite class of rocks. I grew up in central Texas in an area of limestone and fossils. Since my first fossil discovery at age 6, I have been interested in how rocks with obvious sea creatures could be found in terrains that are about 800 feet above sea level. What created that original environment? How did those fossils get trapped there? And why were they at my home? Sedimentary rock is rock that forms at or near the Earth's surface in one of several ways. 1. By the cementing together of loose clasts that were produced by physical or chemical erosion of pre-existing rock. 2. By the growth of shell masses or the cementing together of shell and shell masses. 3. By the accumulation and subsequent alteration of organic matter derived from living organisms. Or 4, by the precipitation of minerals directly from surface water solutions. Layers or bed of sedimentary rock are like the pages of a book. As the sediments are deposited in basins such as river valleys, lakes, seas, and oceans, flora and fauna die, recording the ancient events and environments of the ever-changing surface of the earth. It is like a book into the past. The sedimentary rock occur only on the upper part of the crust, where they form a cover that buries the underlying basement of igneous and metamorphic rock. In this lecture, we will see how sedimentary materials can be buried and transformed into sedimentary rock, be introduced to various specific types of sedimentary rock, show how geologists use the study of sedimentary rocks to characterize Earth system history, and finally discuss sedimentary basins in which thick successions of sedimentary rock accumulate. There are 4 major classes of sedimentary rock that are based on their mode of origin. 1. Clastic sedimentary rock consists of cemented together clasts, solid fragments, and grains broken off of pre-existing rock. Clastic comes from Greek klastos, meaning broken. 2. Biochemical sedimentary rock consists of shells grown by organisms. 3. Organic sedimentary rock consists of carbon-rich relics of plants and other organisms. And 4. Chemical sedimentary rock consists of minerals that precipitated directly from surface water solutions. Same as this formal definition of a sedimentary rock. The answer is C. Geologists sometimes use various adjectives to characterize sedimentary rock composition, such as 1. Siliceous rock contain mostly quartz. 2. Argillaceous rocks contain mostly clay minerals. And 3. Carbonate rocks contain mostly calcite and or dolomite. Approximately 70% to 85% of all sedimentary rocks on the Earth are either siliceous or argillaceous, and 15% to 25% are carbonate, biochemical, or chemical rocks. About 900 years ago, Native Americans inhabited a high plateau called Mesa Verde, as shown in the photograph. In hollows beneath huge overhanging ledges, they built multi-story stone block buildings. The rock feels gritty because it is composed of quartz sand grains cemented together. Geologists call this rock sandstone. Sandstone serves as an example of clastic sedimentary rock because it consists of loose clasts of sand grains that have been cemented together. Production of a clastic sedimentary rock involves 5 steps. Number 1, weathering or breaking rocks into smaller pieces. 2, erosion or removing grains from the parent rock. 3, transportation. dispersed by gravity, wind, water, and ice. 4. Deposition, settling out of the transporting fluid. And 5. Lithification, transforming the sediments into solid rock. Lithification of clastic sediment involves 2 steps. First, once the sediment has been buried, pressure generated by the weight of the overlying material squeezes out the water and air that has been trapped between clasts and presses the clasts together tightly, a process called compaction. Second, during and/or after compaction, cementation binds sediment in place to make coherent sedimentary rock. During cementation, minerals, commonly quartz or calcite or iron, precipitate from groundwater and fill spaces between clasts. The resulting cement acts like glue in that it holds grains together. Say that you pick up a clastic sedimentary rock and want to describe it sufficiently so that another person can picture that rock. What characteristics should you mention? Geologists find the following characteristics most useful: clast size, clast composition, angularity and sphericity, sorting, sedimentary maturity, and character of cement. Each of these characteristics will be discussed on the following slides. Geologists refer to the diameter of the grains making up a clastic sedimentary rock as the clast size or grain size. They range from very coarse to very fine clast size or grain size. Names used for clast size listed in order from coarsest to finest include boulder, cobble, pebble, sand, silt, and mud. Gravels are an accumulation of pebbles and cobbles, and the term mud for an accumulation of wet clay and very fine silt. Another interesting phenomenon is that as transport distance increases, grain size decreases. So the closer you are to the source, the larger the clast size, and the further away from the source, the smaller the clast size. Composition refers to the makeup of clasts in a sedimentary rock. Not all clasts consist of the same type of mineral or rock. Larger clasts, pebbles are larger, typically include rock fragments, meaning that the clasts themselves are aggregates of many mineral grains, whereas smaller clasts, sand, silt, or clay, typically consist of individual minerals. In some cases, lithic clasts, chips of fine-grained rock, may be mixed in with sand grains. Some sedimentary rocks contain clasts of only one composition, but others contain a variety of different kinds of clasts. In the image on the left, we see a conglomerate, which is made up of many different lithic rocks that have been well rounded. So it's part of a stream and was deposited during flood conditions. In the image on the right, we see fine-grained sand particles that have been cemented together by silica. This sandstone contains quartz, which is the clear, shiny materials, and feldspars, or potassium feldspar, which is the pink material. So it is made up of both quartz and feldspar, making it an arcosic sandstone. Angularity indicates the degree to which clasts have smooth or angular corners and/or edges. Sphericity, in contrast, refers to the degree to which a clast has the same dimensions in all directions, so that it resembles the shape of a sphere. In the illustration, we go from angular to subangular to subrounded to rounded. Given time and distance, individual clasts tend to become more rounded or spherical and smoother. So the closer you are and the younger the clasts are, the more angular they are. The further from the source and the longer the length of time that it's traveled, the clast will become more smooth or rounded. Geologists refer to the degree to which the clasts in a rock all have the same size as sorting. Well-sorted sediments consist entirely of clasts of the same size, whereas poorly sorted sediment contains a mixture of more than one grain size. If a sedimentary rock contains larger clasts surrounded by much smaller clasts, for example, cobbles surrounded by sand, then the mass of smaller grains constitutes the matrix of the rock. In the illustration, if transport sifts grains, carrying smaller ones farther and leaving coarser ones behind, grains in the sediment tend to be the same size. In other words, the closer we are to the source, the more poorly sorted the grains are, the further away from the source, and the more time it has to sift and sieve the grains into one size, such as a beach, the more well or very well sorted the sands will be. The term sediment maturity refers to the degree to which a sediment has evolved from being just a crushed up version of its source rock into a well-sorted and well-rounded collection of clasts consisting only of the minerals that are most resistant to weathering. In our illustration, a less mature sediment consists of the fragments of the original rock and contains both resistant and non-resistant minerals. A mature sediment contains only well-sorted, resistant minerals. Not all clastic sedimentary rocks contain the same kind of cement. In some, the cement consists predominantly of quartz, whereas in others, it consists predominantly of calcite. Other kinds of mineral cements do occur, but they are rarer. Classification of clastic sedimentary rock. Class size coarse to very coarse, which is greater than 2 millimeters. Class character, rounded pebbles and cobbles. The rock name is conglomerate. For angular clasts that are greater than 2 millimeters in size, they are called breccia, B-R-E-C-C-I-A. And larger clasts in muddy matrix are called diamictite. From medium to coarse grain size, that is, having 0.07 millimeter to 2 millimeters. Sand-sized grains are all sandstones. Quartz grains only are called quartz sandstones. Quartz and feldspar sand are called arkose, A-R-K-O-S-E. Sand-sized rock fragments are called lithic sandstone. Sand and rock fragments in a clay-rich matrix is called wacke, W-A-C-K-E, or whack, informally called gray whack. Fine, having 0.004 millimeter to 0.06 millimeter class size, are called silt size class, and the rock name is siltstone. Very fine, or less than 0.004 millimeter, or 4/1000th millimeter. Class characters are clay and or very fine silt. Shale is called a shale, is the rock name, if it breaks into platy sheets, and mudstone if it doesn't break into platy sheets. Characteristics of a clastic sedimentary rock provide clues to the source of the sediment and to the environment of deposition. Imagine that large blocks of rock tumble off a cliff and slam into other blocks already at the bottom, such as the talus slope in Figure A, or the figure on the left. The impact shatters the blocks, producing a pile of angular clasts with sharp edges. If these clasts were to be cemented together, the resulting rock would be breccia, as we see in the figure on the right. So breccia is angular rock fragments. The angularity suggests that the rock has little to no transport and that it was deposited relatively close to the clast source. Maybe later a storm causes the clast from the talus slope to slide downslope into a turbulent river. In the moving water, clasts bang into one another and into the riverbed itself, a process that shatters them into still smaller pieces and breaks off their sharp edges. Angular clasts gradually become rounded clasts. When the river water slows, the pebbles and cobbles stop moving and form a mound or gravel bar. Burial and lithification of the gravel bars and of these rounded clasts produce a rock called a conglomerate. So conglomerates are coarse clastic, gravel-sized clasts. Conglomerates, the individual clasts themselves are rounded. Flowing water wears off the corner and edges, and they're deposited further from the source than the breccia. An example of that is river channels in which we find gravel bars, and if those gravel bars become lithified by burial later on and through groundwater moving through them and cement them together, they become a conglomerate. The example on the right. If the gravel stays put for a long time, it undergoes chemical weathering. As a consequence, cobbles and pebbles from the rock break apart into individual mineral grains. For example, disintegration of granite would yield a mixture of quartz, feldspar, and clay. Even slowly moving water can carry clay away and leave behind sand containing a mixture of quartz and some feldspar grains. This sediment, if buried and lithified, becomes arkose. So again, a coarse clastic, sand and gravel sized clasts. Arkose is sand and gravel with abundant feldspar. The feldspar suggests short transport and arid conditions. An example of this would be on the left, the figure on the left, which is an alluvial fan. And if the alluvial fan continues to get buried and lithified, then we end up with an arkosic conglomerate, as seen in the figure on the right. The feldspar grains in sand continue to weather into clay, and eventually, during successive events, that clay washes downstream and leaves behind the durable quartz sand grains. Some of this sand may make it to the sea, where waves carry it to the beaches, and some may end up in desert dunes. Such sediments, when buried and lithified, become quartz sandstones. So sandstones are sand dominated by quartz. An example would be beaches, as we see on the left, or rather dune settings that we see on the left. And then the lithified rock on the right is the sandstone, a quartz sandstone, or a silica sandstone. Silt and clay may accumulate in flat areas bordering streams, regions called floodplains that become submerged only during floods. And some silt and mud settles in a wedge called a delta at the mouth of the river, or in lagoons, protected bodies of quiet water, or in mud flats, broad, quiet areas exposed at low tide along the shores. The silt, when lithified, becomes siltstone and the mud, when lithified, becomes shale or mudstone. So silt-sized sediments form siltstone, and clay-sized sediments form mudstone or shale. Shale breaks into thin sheets. Mudstone doesn't break into sheets. On the left, we have an example of clay and silt sediments in a lagoon. And then on the right, we see the same sediments that have become lithified and form into a shale, which you see the dark colored material that is in sheets and beds or shale. Diamicton is a very poorly sorted sediment that contains cobbles or boulders surrounded by a matrix of sand, silt, and clay. That's the example on the left. When lithified, diamicton becomes a diamictite, the example on the right. Research suggests that diamictites can form from the lithification of debris flow, which is the example on the left. Viscous slurries consisting of mud mixed with larger clays, both on land and underwater, or of glacial till, the debris left behind as glacial ice melts. Whack, a poorly sorted sedimentary rock that consists of sand grains and lithic fragments suspended in a matrix of mud, forms from the deposit of submarine avalanches. Most whack has a grayish color, so geologists informally refer to it as gray whack. So diamictite are large classed in a muddy matrix. An example is a debris flow or glacial till deposit. The example on the left is a debris flow, and the example on the right is a lithified debris flow. And we can tell this by the angular feldspar fragments that are in that gray muddy matrix. Whack is sand and rock fragments in a muddy matrix. An example of that would be a submarine avalanche and deep ocean trench fill. The answer is A. Numerous organisms have evolved the ability to extract dissolved ions from seawater to make solid shells. Some of the organisms anchor to the seafloor, while others crawl or burrow on the seafloor or float in the water above the seafloor. When these organisms die, the solid material in their shells survive, and this material, when lithified, makes up biochemical sedimentary rock. A snorkeler gliding above a coral reef, an example is the one on the left, sees an incredibly diverse community of corals and algae, around which creatures such as clams, oysters, snails, and lampshells live, and above which plankton, including coccolithopores and forams, float. All of these organisms make solid shells out of calcium carbonate, either as calcite or its polymorph aragonite. When the organisms die, the shells remain and may accumulate. Lithification of this sediment yields biochemical limestone, a type of carbonate rock. An example of that is the image on the right. Limestone comes in a variety of textures because the material that forms it has a range of grain sizes and accumulates in a variety of ways. For example, limestone can originate from reef builders such as coral that grew in place, from shell debris that is broken up and transported, or from carbonate mud consisting of plankton shells that settled out like snow out of water. The example A is from shell debris that is broken up and has been transported. Because of this variety, we distinguish among fossiliferous limestone containing fossil shells or shell fragments, as example A, micrite consisting only of very fine carbonate muds, which are example B, and chalk consisting of plankton shells, example C, which is the White Cliffs of Dover. In several locations along the west coast of California and southern Oregon, you will find outcrops of reddish, almost porcelain-like rock occurring in 3 to 15 centimeter thick layers. Such rock forms from plankton such as radiolara and diatoms that produce shells composed of SiO2, silica, which accumulates along with clay to form a siliceous ooze on the sea floor. Gradually, the shells dissolve, forming silica solutions which fill pores in the surrounding clay. Eventually, as tiny crystals grow from these solutions, the sediment lithifies to become rock. Geologists refer to this rock either as biochemical chert to emphasize that it forms from the shells of organisms, or as bedded chert to emphasize that it crops out as a succession of layers. Chert can come in a variety of colors depending on the impurities that it contains. For example, chert contains traces of iron oxide tends to be red. Such chert is also known as jasper. There are two forms of organic sedimentary rocks that geologists recognize: coal and the oil shale. Coal is made up of organic carbon, which is the soft tissue of living things. They are the altered remains of fossil vegetation that are found in lush tropical environments such as swamps, where we have anaerobic conditions. So once the plant dies, it falls to the bottom of the water, and because it's anaerobic, it doesn't decompose, and the materials keep stacking on top of one another. And if that gets buried by sediments, it becomes lithified. And once it becomes lithified, then it alters into coal, which is found in several different forms: peat, lignite, and bituminous coal, which are sedimentary rocks. And then there's anthracite, which is a metamorphic rock. Oil shale, like all shales, contain not only clay, but also between 15 and 30% organic material in a form called kerogen. The kerogen in oil shale comes from the fats and proteins that made up the living parts of plankton or algae. After dying, the tiny organisms settle in an environment where they do not immediately rot away or get eaten, in other words, an anaerobic environment. They mix with clay minerals and mud. When the mud gets buried and lithified, the ocean material undergoes chemical reaction that transforms it into kerogen. The process of organic materials colors oil shale black. Chemical sedimentary rocks typically have a crystalline structure that formed partly during their original precipitation and partly when at a later time new crystals grow at the expense of old ones through the process of recrystallization. There are several classes of chemical sedimentary rocks that we will be discussing: evaporites, travertine, dolostone, and chemically precipitated chert. Evaporites are layered crystalline sedimentary rocks that form from brines generated in areas where the amount of water lost by evaporation exceeds the total amount of water from rainfall and influx via rivers and streams. Salt precipitation occurs in desert lakes with no outlets or along the margin of restricted seas. For thick deposits of salts to form, large volumes of water must evaporate. This may happen when plate tectonic movements temporarily cut off arms of the sea, as we saw in the Mediterranean Sea in Interlude B, continental rifting when seawater first begins to spill into rift valleys. When 80% of the seawater trapped in a basin evaporates, gypsum forms, and when 90% of the water evaporates, halite precipitates. If seawater were to evaporate entirely, the resulting evaporite would consist of 80% halite, 13% gypsum, and 7% other salts and carbonates. In the figure, in lakes with no outlet, tiny amounts of salt brought in by streams stay behind as the water evaporates. When the water evaporates entirely, a white crust of salt remains. And what we're looking at is salt on the floor of Death Valley, California. One form of chemical sedimentary rock, limestone, is travertine. Travertine consists of crystalline calcium carbonate, CaCO3, that precipitates directly from groundwater that is seeped out at the ground surface, either in hot or cold water springs or on the walls of caves. What causes this precipitation? It happens in part when the groundwater degasses, meaning that some of the carbon dioxide that had been dissolved in it bubbles out of solution. Removal of carbon dioxide decreases the ability of the water to hold dissolved carbonate. Precipitation also occurs when water evaporates, thereby increasing the concentration of carbonate, or it causes a superconcentration of carbonate. Recent research suggests that various kinds of microbes can accelerate the process of precipitation. In the figure on the left, we see travertine accumulated in terraces at Mammoth Hot Springs in Yellowstone National Park in Wyoming. And on the figure on the right illustrates travertine speleothems formed as calcite-rich water drips from the ceilings of Timpanogos Cave in Utah. Not all carbonate rock consists of pure calcite. A variety of carbonate rock called dolostone differs from limestone in that it contains the mineral dolomite, calcium magnesium carbonate, CaMg, CO3, and 2. Where does the magnesium in dolomite come from? Dolomite is formed by a chemical reaction between solid calcite and magnesium-bearing groundwater. This change may take place beneath lagoons along a shore soon after the limestone forms, or a long time later after the limestone has been buried deeply and the magnesium is carried in the groundwater and replaces the calcium in the limestone. In the figure on the left, we see a dolomite quarry, and then a figure on the right shows a close-up of dolomite. Dolomite's a lot harder than limestone, and doesn't fizz as much when you apply calcium, when you apply hydrochloric acid to it. A variety of carbonate rock called dolostone differs from limestone in that it contains the mineral dolomite, which is a calcium magnesium carbonate. Where does the magnesium in dolomite come from? Dolomite is formed by a chemical reaction between solid calcite and magnesium-bearing groundwater. This change may take place beneath lagoons along a shore soon after the limestone forms, or it may occur a long time later after the limestone has been buried deeply and is changed by groundwater bearing magnesium carbonate, or rather groundwater bearing magnesium. On the image on the left, we see a dolomite quarry, and then on the right, we see a close-up of dolomite. When you test for dolomite, the difference between dolomite and limestone is that when you apply hydrochloric acid to dolostone or dolomite, it doesn't fizz quite as much as the limestone would, because it's been the calcium has been replaced by magnesium. In the middle image, we see close-up of a black chert nodule surrounded by white chalk exposed on a cliff in southern England. The chert nodules grew when microscopic quartz crystals gradually precipitated and replaced calcite crystals within a bed of limestone. Because of its mode of formation, geologists refer to this type of chert as replacement chert. Because replacement chert commonly occurs in nodules, it is also known as nodular chert. Replacement chert doesn't form only in limestone. Some grows in buried silica-rich volcanic ash beds when the silica in groundwater precipitates as microcrystalline quartz within wood that has been buried by the ash, forming petrified wood, the figure on the left. The quartz gradually replaces the interiors of the wood cells as the cell walls convert into carbon and other minerals. Because of this delicate replacement process, the chert retains the shape of the wood and the growth rings within it, so the resulting solid block of rock still looks like wood. Not all chemically precipitated chert replaces other minerals. A type of chert known as agate precipitates in concentric rings inside open hollows in a rock. Commonly, the successive rings of chert have different colors, giving the rock a striped appearance, as we see in the figure on the right. These colors are caused by variations in the type and concentrations of impurities. In the figure in the middle, we see a close-up of a black chert nodule surrounded by white chalk exposed on a cliff in southern England. This is chert nodulars grew when microscopic quartz crystals gradually precipitated and replaced calcite crystals within a bed of limestone. Because of its mode of formations, geologists refer to this type of chert as replacement chert. Because replacement chert commonly occurs in nodules, it's also known as nodular chert. Replacement chert doesn't form only in limestone. Some grows in buried silica-rich volcanic ash beds when the silica in groundwater precipitates as microcrystalline quartz within wood that has been buried by the ash, forming petrified wood, as we see in this example on the left. A 14-centimeter diameter log of petrified wood from Wyoming formed about 50 million years ago. The quartz gradually replaces the interiors of the wood cells as the cell walls convert into carbon and other minerals. Because of this delicate replacement process, the chert retains the shape of the wood and the growth rings within it, so the resulting solid block of rock still looks like the wood. Not all chemically precipitated chert replaces other minerals. A type of chert known as agate precipitates in concentric rings inside open hollows in a rock. As we see in this image on the right, a thin slice of Brazilian agate lit from the back that shows growth rings. Commonly, the successive rings of chert have different colors, giving the rock a striped appearance. These colors are caused by variations in the type and concentrations of impurities. The answer is D, mineral composition. D, mineral composition. When you look at a large outcrop of sedimentary rock, you'll notice that the outcrop displays distinct layers, as this image below shows. Differential weathering makes stratification stand out. It's clear even from a distance that these hills near Las Vegas, Nevada consist of sedimentary rock. On the surfaces of layers, you may see small ridges and/or indentations, and within the layers, the grains may be sorted or oriented so as to define distinct textures. These features, which range from subtle to obvious, form during the process of deposition, and, as we will see, provide key clues to the environment in which the sediments were deposited. Geologists use the term sedimentary structure for such features. A single layer of sediment or sedimentary rock with a recognizable top and bottom is called a bed, B-E-D. The boundary between two beds can be called a bedding plane. Several beds together constitute strata. A singular stratum from the Latin stratum, meaning pavement, and the overall division of sediment into a sequence of beds is bedding or stratification. So a single layer is called a bed. If we have two layers together, the interface between the two beds is called a bedding plane. If we have several beds together, that constitutes strata. And the overall division of sediment into a sequence of bed is bedding or stratification. Why does bedding form? To find the answer, we need to think about how sediment accumulates. Changes in climate, water depth, current velocity, or the sediment source control the type of sediment deposited at a location at a given time. For example, on a normal day, a slow-moving river may carry only silt, which collects on the river bed. During a flood, the river flows faster and carries sands and pebbles, so a layer of sandy gravel forms over the silt layer. Then when the flooding stops, more silt buries the gravel. If this succession of sediments becomes lithified and exposed for you to see, the layers appear as alternating beds of siltstone and sandy conglomerate. Bedding is not always well preserved, for in some environments, burrowing organisms disrupt the layer. Specifically, worms, clams, and other creatures can churn sediment and leave behind burrows. This process is called bioturbation. Over geologic time, long-term changes in a depositional environment may take place, so a given sequence of strata may differ markedly from sequences of strata above or below. A sequence of strata distinctive enough to be traced across a fairly large region is called a stratigraphic formation, or simply a formation, as we see in figure on the left. For example, a region may contain a succession of alternating sandstone and shale beds deposited by rivers, overlain by beds of marine limestone deposited later when the region was submerged by the sea. A geologist might identify the sequence of sandstone and shale beds as one formation and the sequence of limestone beds as another. Formations may be named after the locality where they were first found and studied. A geologic map portrays the distribution of stratigraphic formations in a region, like we see in the image on the right. Many clastic sediments accumulate in moving fluids, wind, river, and waves. Fascinating sedimentary structures develop at the interface between the sediment and the fluid. These structures, known as bed forms, reflect factors such as the velocity of the flow and the size of the class. Though there are many types of bed forms, we'll focus on only two: ripple marks, which are small, a few centimeters in height, and dunes, which are much larger, measuring meters to hundreds of meters in height. Ripple and dunes develop perpendicular to flow. One direction of flow creates asymmetrical ripples and dunes that are used to determine flow directions in ancient sediments. We find this in rivers, where direction of flow is always in the same direction. If we have two directions of flow, such as wave action in nearshore marine environments, then we end up with symmetrical or symmetric ripples and dunes. The windward slope faces upwind. It is an erosional surface that we will discuss on the next slide. Next is the crest or top edge of the slip face. Next is the steep leeward slip face. It slopes downwind from the prevailing wind current. The base of the slip face is the toe of the slip face. Note the asymmetrical ripples that have developed on the windward slope. If you examine a vertical slice cut into a ripple or dune, you will find distinct internal laminations inclined at an angle to the boundary of the main sedimentary layer. Such laminations are known as crossbeds. Imagine a current of air or water moving uniformly in one direction. The current erodes and picks up clasts from the upwind or upstream part of the bed form and deposits them on the leeward part. Sediment builds up on the leeward side until gravity causes it to slip down. With time, the leeward side of the bed form builds in the downstream direction. The surface of the slip face establishes the shape of the crossbeds. Eventually, a new cross-bedded layer may build out over a pre-existing one. We refer to the boundary between two successive layers as the main bedding, the image on the right, and the internal curving surfaces with the layer as the cross-bedding. Sediment deposited on a submarine slope might not stay in place forever. For example, an earthquake or storm might disturb this sediment and cause it to slip down slope and mix with water to yield a murky, turbulent cloud. This cloud is denser than clear water, so it flows down slope like an underwater avalanche. Such a flow is known as a turbidity current. Down slope, the turbidity current slows and the sediment that it carried starts to settle out. Larger grains sink faster through a fluid than do finer grains, so the coarsest sediments settle out first. Progressively finer grains accumulate on top, with the finest sediment, clay, settling out last. This process forms a graded bed, that is, a layer of sediment in which grain size varies from coarse at the bottom to fine at the top. Geologists refer to a deposit from a turbidity current as a turbidite. You can find a turbidite in Eddyville on Highway 20. On the left-hand side, you'll see an outcrop of rock with light-colored materials and then dark-colored materials. The light-colored material is siltstone and the dark material is claystone. And these are turbidity currents that flowed off of a delta down a canyon to that location from the Klamath Mountains in Eocene time. A number of features may appear on the surface of a bed as a consequence of events that happened during deposition or soon after. These bed surface markings may include mud cracks, scour marks or flute casts, fossils, and paleosols. The first one we're going to look at on this slide are mud cracks. If a mud layer dries up after deposition, the figure on the left, it cracks into roughly hexagonal plates that typically curl up at their edges. We refer to the openings between the plates as mud cracks. If buried and mud cracks can be preserved, then they look like the image on the right in the rock record. As current flows over a sediment surface, such as a stream, they may erode small troughs called scour marks parallel to the current flow, as we see in the example on the left, or the image on the left. When these indentations are buried and lithified, then they form flute casts. And these flute casts indicate the bottom of the bed. So here in the example on the left, we know we're looking at a stream bed. We also know that that is the bottom of the formation. Fossils are relics of past life. Some fossils are shell imprints, footprints, or feeding traces on a bedding surface. If we see footprints or feeding traces on the bed, then we know that we're looking at the surface of the bed. Otherwise, what it can tell us is a little bit about the history of the rock. For example, the image on the right, we see the brachipod spirifer, which lived in Pennsylvanian time. And so this tells us that this particular rock, no matter where it is in the world, comes from Pennsylvanian time. The fourth example is paleosols. If a soil that formed on the surface of a sedimentary bed becomes buried, it can be preserved as a paleosol. If lithified, a paleosol may delineate a bed surface because it has a different texture and in some cases a different color than does the internal portion of the bed. And if you look at figure 717D in your book, you will see a paleosol between two sandstone beds. So that tells you that that is the top of one bed, or another way is the bottom of the upper bed is marked by the paleosol. Geologists refer to the conditions in which sediment was deposited as a depositional environment. To identify the depositional environment in which ancient sedimentary strata accumulated, geologists look for clues. A geologist examines grain size, class composition, sorting, bed surface marks, cross-bedding, and fossils to identify a depositional environment. With experience, a geologist can determine whether a succession of beds accumulated at the end of a glacier, in a desert, on a river floodplain, along a beach, in shallow seawater just offshore, or on the deep sea floor. Terrestrial depositional environments are those that develop inland, far enough away from the ocean shoreline that ocean tides and waves do not affect them. The sediment of terrestrial deposits settle on dry land or under and adjacent to freshwater streams, glaciers, and lakes. The first one we're going to look at is glacial environments. Solid ice can move sediment of any size. So as the glacier moves down a valley in the mountains, it carries along all the sediment that falls on its surface from adjacent cliffs or gets plucked from the ground at its base or sides. At the end of the glacier, where the ice finally melts away, it drops its sedimentary load and produces a pile of glacial till, as we see in this image here. Till is unsorted and unstratified. It contains clasts ranging from clay size to boulder size, all mixed together, and therefore becomes a type of diamicton. Mountain stream environments. As we walk beyond the end of the glacier, we enter a realm where turbulent streams rush down slope in steep-sided valleys. This fast-moving water has the power to carry large clasts. In fact, during floods, boulders and cobbles can tumble down the stream bed. Between floods, when water flow slows, the largest clasts settle out to form gravel and boulder beds, while the water carries finer sediments such as sand and mud further downstream, as we see in this image here. Sedimentary deposits of a mountain stream would therefore become breccia and conglomerate depending on the degree of rounding. In arid regions where there is not enough water for the stream to flow continuously, the stream deposits its load of sediment on the plain near the mountain front, producing a wedge-shaped apron of gravel and sand called an alluvial fan, as we see in our example in the image on this slide. Deposition takes place here because when the stream emerges from a canyon mouth, it spreads out over a broad area. So friction with the ground causes the water to slow down, and moving water does not have the power to move pebbles, cobbles, or coarse sediment. Notably, the sediment in the sand of alluvial fan is derived from the erosion of granite. Therefore, it may still contain feldspar grains that have not yet weathered into clay. As a consequence, alluvial fan sediments become breccia, conglomerate, and arkose sandstone. In very dry climates, few plants can grow, so the ground surface lies exposed. Strong winds can pick up dust and sand from the surface. The dust gets carried away, and the remaining well-sorted sand may accumulate in large dunes, as we see on the image on the left. Thus, thick layers of well-sorted sandstone in which we see large crossbeds are relics of desert sand dune environment. In places, deserts contain low areas in which water collects during floods, but dries up between floods. Salts precipitate in such settings and can build into beds of evaporites. So in the image in the middle and on the right, we see playas, which are low-lying depressions in which we have a lot of evaporations, and we see salt and anhydrite being deposited or having been deposited in these playas. Image on the right shows that in some cases prevailing winds are strong enough that they can blow rocks from the edge of the playa all the way out to the middle of the playa on that slick surface of anhydrite. In climates where stream flows, we find several distinctive depositional environments. Rivers transport gravel, sand, silt, and mud. The coarser sediment tumbles along the bed in the river's channels and collects in cross-bedded ripple layers, while the finer sediments drift along suspended in the water. This fine sediment settles out along the floodplains. Mud layers on the floodplain dry out between floods, leading to the formation of mud cracks. River sediments lithify to form sandstone, siltstone, and shale. Typically, channels of coarse sediment are surrounded by layers of fine-grained floodplain deposits. In cross-section, this channel has a lens-like shape. Geologists commonly refer to river deposits as fluvial sediments, from the Latin word fluvius, meaning river. In temperate climates where water remains at the surface throughout the year, lakes form. In lakes, the relatively quiet water can't move coarse sediment. Any coarse sediment brought into the lake by a stream settles out at the stream's outlet and forms a delta. Only fine clays make it out into the center of the lake where it settles to form mud on the lake bed. Not surprisingly, lake sediments typically consist of finely laminated shale called varves. The light-colored is silt and the dark-colored is mud. And so the light indicates periods of high rainfall when sediments are transported further out into the lake, and the dark represent periods of low rainfall when only fine sediments are carried out into the lake. A light and dark sequence indicates one varve, which indicates 1 year. So we can core through sediments in a lake and count the number of years that the sediments have been accumulating on the bottom of the lake. A delta is a wedge shape, or is a wedge of sediment that accumulates where moving water enters standing water. Deltas were named because the map shape of some deltas resemble the Greek letter delta. Along the seashore, a variety of distinct coastal depositional environments develop. The character of each reflects the nature of the sediment supply and the climate. Marine depositional environments start at the high tide line and extend offshore to the deep sea floor. Once the river reaches the ocean, the river water stops flowing, so water velocity slows and the sediments settle out to build a delta into the sea. Large marine deltas are very complex. For marine deltas host many different sedimentary environments, including swamps, channels, floodplains, and submarine slopes. Sea level changes may cause the position of the different environments to move inshore or offshore with time. As a result, the deposition of marine delta produce a great variety of sedimentary rock types. Ocean currents transport sands from the end of the delta along the coastline. The sand washes back and forth in the surf, so it becomes well sorted. As waves winnow out mud and silt, it becomes well rounded. And because of the back and forth movement of the ocean water, the sand surface may become rippled. So if you find well-sorted, medium-grained sandstone, perhaps with ripple marks, you may be looking at the remnants of a beach environment. From the beach, we proceed offshore. In deeper water, where wave energy does not stir the sea floor, finer sediments can accumulate. Because the water here may be only meters to a few tens of meters deep, geologists refer to this depositional setting as a shallow marine environment. Clastic sediments that accumulate in this environment tend to be fine-grained, well-sorted, well-rounded silt. A great variety of organisms, such as mollusks, gastropods, and worms, live in or on this sediment. Therefore, if you see beds of siltstone and mudstone containing marine fossils, you may be looking at shallow marine clastic deposits. In the example, or in the photograph, the dark material on the bottom is the Nye Beach mudstone, and it is made up of mainly very fine-grained silts and well-rounded silts, which represent shallow marine clastic deposits. And then overlying that is the Uinta Formation, which is a deltaic formation. In shallow marine settings where relatively little sand and mud enter the water, the warm, clear, nutrient-rich water can host an abundance of organisms with carbonate shells, which become carbonate sediments, as we see in the figure on the left. Beaches collect sand and composed of shell fragments. Lagoons are sites where carbonate mud accumulates. And reefs consist of coral and coral debris. Further offshore from a reef, we can find a sloping apron of reef fragments. Shallow marine carbonate sediments transform into various kinds of limestone. So in the figure on the left, we see calcite sand beaches. We see a lagoon that has calcite mud and calcite sands mixed together. We see the reef proper itself, the living reef. And then we see the forereef area, or which is also called the reef face, where broken pieces of the reef slide down to the ocean floor. In the figure on the right, we see a reef surrounding an island in the tropical Pacific. We conclude the journey by sailing far offshore. Along the transition between the coastal region and the deep ocean, turbidity currents deposit graded beds. In the deep ocean realm, only fine clay and plankton provide sources of sediment. The clay eventually settles out onto the deep sea floor, forming deposits of finely laminated mudstone. And plankton shells settle to form chalk from calcite shells, as we see in the figure on the left, which are Globigerinoes plankton. Or they can form chert from siliceous shells. Deposits of mudstone, chalk, or bedded chert therefore indicate a deep marine origin. In the figure on the right, we see the white cliffs of Dover, which are made up of Globigerina plankton, indicating a deep marine deposits. Geologists use the term subsidence to refer to the process by which sinking takes place, sinking within the lithosphere takes place, and the term sedimentary basin for the resulting sediment-filled depression. We also distinguish among the different kinds of sedimentary basins on the basis of the region of a lithospheric plate in which the basin forms, as defined in the context of plate tectonics theory. Rift basins form in continental rifts, regions where the lithosphere has been stretched. During rifting, the surface of the Earth subsides simply because the crust becomes thinner as it stretches. To picture this process, imagine pulling on either end of a block of clay or taffy with your hands. As the clay or taffy stretches, the central region of the block thins and sinks lower than the ends. As the rift grows, slip-on faults send blocks of crust downward, producing low troughs bordered by narrow mountain ranges. Alluvial fan deposits form along the bases of the mountains, and salt flats or lakes develop in the interior portions of the troughs. Passive margin basins form along edges of continents that are not plate boundaries, such as the east coast of North America. They are underlain by stretched lithosphere, the remnants of a rift whose evolution successfully led to the formation of a mid-ocean ridge. Passive margin basins form because thermal subsidence of stretched lithosphere continues long after rifting ceases and seafloor spreading begins. These basins fill both with sediment carried to the sea by rivers and with carbonate sediment formed in coastal reefs. Sediment in a passive margin can reach an astounding thickness of 15 to 20 kilometers or 15,000 to 20,000 meters. Intracontinental basins develop in the interior of continents, initially because of subsidence over a rift. They may continue to subside in pulses, even hundreds of millions of years after they first formed, for reasons that are not yet well understood. Illinois and Michigan are each underlain by an intracontinental basin, the Illinois Basin and the Michigan Basin, respectively, in which up to 7 kilometers of fluvial deltaic or shallow marine sediment accumulated. At times, extensive swamps formed along the shorelines of these basins. The plant matter of these swamps transformed into coal when it was later buried deeply. Foreland basins form on the continental side of a mountain belt because the forces produced during the convergence or collision pushes large slices of rock up faults and onto the surface of the continent. The weight of these slices pushes down on the surface of the lithosphere, producing a wedge-shaped depression adjacent to the mountain range that fills with sediment eroded from the mountain range. Fluvial and deltaic strata accumulate in foreland basins. Changes in sea level relative to the land surface can control the succession of sediments that we see in a sedimentary basin. At times during Earth's history, relative sea level has risen by as much as a couple of hundred meters, creating shallow seas that submerge the interiors of continents. At other times, relative sea level has fallen by a couple of hundred meters, exposing the continental shelves to air. Global sea level changes may be due to a number of factors, including climate change, that control the amount of ice stored in polar ice caps and cause changes in the volume of ocean basins. Sea level at a location may also be changed by a local uplift or by sinking of the land surface. When relative sea level rises, the shoreline migrates inland. During this process, known as transgression, coastal sediments progressively bury terrestrial sediments, and deeper water sediments bury coastal sediments. When relative sea level falls, the coast migrates seaward. We call this process regression. Typically, the record of a regression will not be well preserved because as sea level drops, areas that have been sites of deposition become exposed to erosion. A succession of strata deposited during a cycle of transgression and regression is called a depositional sequence. Lithification represents an aspect of a broader phenomenon called diagenesis. Geologists use the term diagenesis for all the physical, chemical, and biological processes that transform sediment into sedimentary rock and that alter characteristics of sedimentary rock after the rock is formed. In sedimentary basins, sedimentary rocks may become buried very deeply. As a result, the rocks endure high pressures and temperatures and come in contact with warm groundwater. Diagenesis under such conditions can cause chemical reactions in the rocks that produces new minerals and can also cause cement to dissolve or precipitate. As temperatures and pressures increase with depth, the changes that take place in rocks become more profound. At sufficiently high temperatures and pressures, metamorphism begins. A new assemblage of minerals form, and the mineral grains may become aligned parallel to one another. The transition between diagenesis and metamorphism in sedimentary rocks occur between temperatures of 150 degrees and 300 degrees centigrade. In the next chapter, we will enter the realm of true metamorphism.